This next talk will not be a publication, but rather my own thoughts, titled LSD from a Three-Dimensional Perspective. The inspiration for this talk comes back to my undergraduate days taking organic chemistry, in which you really begin to understand the idea that molecules are not these flat planar things that we like to assume they are when we look at them on a piece of paper. Although really small, they do have three dimensions to them, and thus we should treat them as so. Before we get to what LSD looks like in a three-dimensional space and what implications it has, let's look at an example of a much simpler compound. Let's look at ethane. Ethane has a formula of C2H6. We have 2 carbons and a total of 6 hydrogens. Notice how this is just one-dimensional. It just tells us that it's really a line. It doesn't tell us anything about the connections of the lines and the atoms. Now let's look at ethane in 2 dimensions. This is the 2-dimensional shape of ethane. It shows that we once again have 2 carbons connected by a total of 6 hydrogens, but it tells us more about the spatial orientation of this. Let's now look at ethane in a 3-dimensional space because we still don't know anything about the depth of the molecules. This is ethane in 3 dimensions, and once again we have 2 carbons connected by a bond and a total of 6 hydrogens connected by a bond. Now what this tells us is something a little bit different and interesting. It's that we can actually figure out how many degrees are in between each of those hydrogens connected to each carbon. We can figure this out by taking 360 and dividing it by 3, which would give us 120 degrees. So it's telling us that there's 120 degrees between each one of those hydrogen atoms. But we still don't know much about how the front and the back of the atom are related, so let's keep going with this analogy. Let's now look at the three-dimensional implications of this. If we take the same molecule ethane and line up the 2 carbons, we would see the back carbon is directly behind the front carbon, and thus we don't see the bond. This conformation is known as the staggered conformation, and in fact it is the most stable conformation, because electrons are negatively charged, which are in the atoms, and those want to be as far away from each other as possible, much like a person you don't like. In between every front hydrogen and back hydrogen, there is a 60 degrees. This can be found by taking 360 and dividing it by 6. If we were to grab one of these bonds, or front carbons, and rotate it 60 degrees, we would get this conformation. This is known as the ethane eclipsed conformation, and it is the least stable because there is 0 degrees between every front hydrogen and back hydrogen. Let's now take this one step further, and if any of you have taken organic chemistry, you've probably seen this exact example in your class. This is the eclipsed versus staggered ethane energy profile. Don't let all the fancy words confuse you. Let's talk it through. On the x-axis, we have 0 degrees, 60 degrees, 120, and 180. This just represents the degrees that are in between the front hydrogens and the back hydrogens. We said there was a 60-degree rotation in between each conformation. If we start with 0 degrees between every hydrogen, we would see the eclipsed conformation, which we said was the least stable and thus highest in terms of the potential energy, much like a very, very hyper kid that doesn't want to calm down. If we then grab that carbon in front and rotate it 60 degrees slowly, we would see the staggered conformation of ethane, which is the most stable, indicated by the lowest dip in the energy level. This would be the equivalent of a very chilled out kid. We can think about it as if you take the eclipse version and slowly rotate that bond, the energy drops and drops and drops until you hit that 60-degree rotation, which gives you the most stable conformation of ethane. On the right here, we see 12.6 kilojoules per mole. This is the energy cost in going from the highest energy conformation to the lowest energy conformation. In so, the eclipsed and staggered conformations have a difference in 12.6 kilojoules per mole. And the last idea we need to cover before we get to our fun compound, LSD, and look at its three-dimensional applications in space. Let's look at which bonds can rotate in chemistry and which ones are unrotatable or can't rotate. We saw that with the compound ethane. ethane is connected by a carbon-carbon single bond. It's kind of like if I took a stick and put a basketball at each end, and I could rotate those basketballs around their axis. This would be fine, and it wouldn't break the bond. And thus we can say single bonds in chemistry have the availability to rotate, as we saw with the eclipsed and staggered conformation. If I then made this compound called ethene and put two sticks, and then I put a basketball at each end of two sticks, if I tried to hold one basketball in place and rotate the other basketball, I would break the sticks, i.e. the bond would break. And thus, double bonds cannot rotate. They are pretty rigid in terms of a chemistry sense. Now this compound, this is ethine, or acetylene, which always confuse me. This is a carbon-carbon triple bond. This is the equivalent of taking 3 sticks and putting a basketball at each end. If I tried to rotate one basketball while holding the other one in place, I would break the sticks, and i.e. the bond would break. Thus in chemistry, triple bonds cannot rotate. They are very rigid. Now this compound is a carbon-carbon bond in a ring. This compound is known as cyclohexane. Now cyclohexane, because it is connected in a ring, it's kind of like imagine the basketball as each blob in the middle, and the bond is connecting it around in a ring. If you guessed it right, if I tried to grab one of the carbons and hold any other carbon in place and try to rotate it, the bonds would break. Therefore, single bonds in a ring cannot rotate. Now, if you've taken organic chemistry, you've probably drawn many benzene rings, this next compound. This is a single double alternating bond in a ring. This is even more rigid than cyclohexane. Double bonds in a ring cannot rotate. And finally, let's look at a more in-depth analysis of the LSD structure. This structure you've seen at the beginning of this video and other of my videos. This is known as a line structure. It's a shorthand method organic chemists use to simplify structures. We don't always draw the hydrogens and carbons in a lot of these structures. This is a simplified version, but there are implicit meanings where hydrogens and carbons are. For example, when a line ends, this always means that there is a carbon. Carbon has this availability of being able to attach to 4 different things. If it is already occupied by one bond to the nitrogen, that means that it has 1 carbon, and the remaining 3 bonds will be hydrogens that aren't written. What about a junction? These are where 2 lines meet. At every point where 2 lines meet, there's always a carbon, and if there are 2 bonds remaining out of the 4 that carbon can have, it must mean that there's 1 carbon and 2 hydrogens. Another example might be, well, what about if we have 3 things bonded to carbon, as in this benzene ring? Because this carbon is already occupied by 3 bonds and can have a total of 4, it must mean that there is 1 carbon and 1 hydrogen at this junction. Lastly, this junction, if we count the bonds around the intersection, that middle intersection has 4 different things attached to the carbon. If carbon can only bond to 4 things, it must mean that there is 1 carbon and no or 0 hydrogens. And finally, let's look at the rotatable bonds within the molecule. We talked about this idea that if there's a single bond, that means that the bond can rotate. And if there's a double bond, it must mean that it can't rotate. And we said that things in ring structures, rings are very rigid and cannot rotate. Now before I proceed in the video, you should pause it and see if you can figure out which bonds are rotatable before we move on. Okay, now that you've hopefully paused the video and tried this yourself, here's what we might see. Well, this whole ring has a bunch of double bonds and it's a ring. Rings cannot rotate, we said. Thus, this part of the molecule is very rigid. No rotation can occur within it. Technically, there's a bond right here that can rotate. But the rotation here actually doesn't really mean that much in 3-dimensional space. Because it's just rotating in the same spot, it's not going to change really the orientation of the hydrogens too much, although it will a little bit. So it should be considered. Now, the next possible spot of rotation is right here, near the acid part of the molecule, highlighted in blue. This is a single bond to another carbon. Thus, this whole thing can rotate in 3-dimensional space. If we go just a bond up to the next carbon, that is also single bonded to a nitrogen. This whole part of the molecule can also rotate. The next two spots of rotation are within the diethylamide moiety, which is what I talked about in my last video in terms of the drug's potency. This was responsible for LSD being such a potent drug, the diethylamide moiety. It has a lot of rotation within three-dimensional space because there are two carbons coming off of the nitrogen. And lastly, these two bonds can rotate. The ethyl part of the group, the diethyl part of the moiety, can actually rotate. This causes some interesting implications that we'll look into in a later slide. Let's now look at LSD's various conformers. These are the rotations that it can go through in space to give us different orientations. The program I use is called Spartan. It can generate these pretty quickly. Generally how the program works is you tell the program to rotate each single bond in the molecule until it arrives at the lowest energy one. The lowest energy conformer will be the one where the electrons or bonds are furthest away from each other. This is very hard to do with the naked eye, so we generally have high-powered computer programs do this for us. In the first picture on the left, we see LSD. It has an ergoline ring system. Most ring systems are very rigid and thus cannot move, which is why we observe in the other two conformers it's in the same exact orientation in space. Let's now look at one of the single bonds in the molecule. There's a single bond right in this position. The orientation in space shows us that the oxygen is right behind the single bond. In the next molecule, we see this also. The rotation is causing the oxygen to be about 45 degrees of that in the first molecule. If we go to the third molecule, it's kind of like the first molecule. The oxygen is almost directly behind it, but not quite. It's angled just a little bit. We should also note the top parts of the molecule. There are two diethyl groups coming off of the nitrogen. Each of those ethyl groups can also rotate because they are just bound by single bonds. Let's consider the ethyl group that is pointing into the plane of the page and to the right. This one right here. This one is pointing in and to the right. If we compare that to the second picture has the ethyl group 180 degrees different of the first picture. And the third picture is kind of like the second picture, where the ethyl group is pointing in and to the left. We're not going to consider the other ethyl group because the three-dimensional orientation in space is quite similar. Let's now take a look at LSD's various conformers from a different angle. This angle is from the side. You can almost imagine if I grab the ergoline ring system and rotate it 90 degrees, this would be the orientation in space of that viewing angle. The nice part about Spartan is it can automatically generate these values of which conformer is the lowest and thus which one will bind to the receptor, or i.e. is more likely to bind to the receptor. This first conformer has an energy value of 348.26 kilojoules per mole. The idea here being that the one with the lowest energy conformer closest to 0 is going to be the one that docks to the receptor. The second conformer has an energy value of 350.93 kilojoules per mole, about 2 kilojoules per mole higher than that of the first calculated energy value. And the third conformer has an energy value of 351.42 kilojoules per mole. Because the lowest energy value is 348.26 kilojoules per mole, we would expect that this is the conformer that binds to the serotonin receptors. And lastly, the key points of this video are as follows. Atoms and molecules want to be as far away from each other as possible. We saw this with the staggered and eclipsed conformation of ethane. Molecules occupy every possible conformer, but statistically, the chances of it occupying its lowest energy conformer is much higher than the possibility of it occupying a high energy conformer. For example, if you could take the LSD molecule and tell it to freeze in one conformer, you are thus more likely to see it in a lower energy conformer than a higher energy conformer. In a later video, we'll look at what happens when LSD binds to receptors inside of our brain, and look at how all that fun jazz works.